Okay, I think it's almost time, so the students please be seated. And for the second lecture for today, it's my honor to introduce Professor Kuboyama. Professor Kuboyama is currently an assistant professor in the School of Materials and Chemical Technology, Tokyo Institute uh, of Technology. Okay, and his research focus in the control and optical properties of polymer blend and the study and morphology and the birefringence of polymers, ferrite, and the composite of polymer and inorganic nanoparticles. And the topic he would like to offer today is the characteristic of polymers. So please join me to welcome Professor Kuboyama.
Thank you for your kind introduction. Today, I'd like to introduce you about the characteristics of polymers because maybe almost most of you, uh, your major is not polymer science. So today, I'd like to introduce you the fundamentals of polymer characteristics. Okay, so let's start from the organic materials. Yeah. The organic materials is consisting of carbon main chain, carbon atom backbone, and
I'm
plus,
sorry, Professor Kubuyama, your
yeah.
slide stops in the first page. Oh, can you use full screen?
Oh, this one is better.
Yeah. Okay,
Okay,
that's
so
fine. Okay,
I'll
thank
use this screen and. Uh, So the polymer chain is consisting of the mainly carbon, but hydrogen and oxygen and nitrogen and so on. And the polymer is a very long chain molecule. And normally you know as polymer as plastics or rubbers, fibers, films, gels, and so on. And establishment of the polymer concept is in, in this slide. I cannot use animation, but okay. So establishment of polymer concept is around 1930, and at, on 1935, the first synthetic polymer is synthesized. That is nylon. And that is the beginning of the era of synthetic polymers. Okay. And as I told you that mainly the polymer is composed of light elements such as carbon and hydrogen and oxygen and nitrogen and so on. So the polymer is lightweight and the polymer is long chain, so that is easy to mold. So that is flexible molecule. So that is soft. So the polymer is sometimes called as soft material. And this one shows viscoelasticity. So this one polymer have shows both properties, elasticity and viscosity. And this one consisting of covalent bonding. So this one have high strength. And polymer is long chain, long molecules. So this one can be easily forms of fiber. And so, and this one can form the many kind of states. So for example, molecular chain is long. So this one can form the amorphous disordered state. And if the molecules packed regularly, so this one form the crystal phase. ちょっといかんかな。 So can I use this image? Okay. Can you see this one? This slide? Is it okay?
Yes.
Ah, okay. So and let me introduce you the polyethylene in the case of the polyethylene. And the polymers are large molecules composed of a repeating structure unit called monomer units, connected by covalent chemical bonds. And in the case of polyethylene, the structure is like this. And maybe you were the high school student, you learned the polymer structure is like this. And from this figure, the repeating unit seems to be a C82. So you may want to call this one as a polymethylene, but this one is normally called as polyethylene because this polymer is synthesized from the ethylene. So the chemical structure is written by like this, and this one is called as polyethylene. So maybe all of you are familiar with polyethylene. So because this one is used as bottle caps, plastic bags, and plastic buckets, and also on. And the chemical structure is like this, but actual polymer is three-dimensional one, not the two-dimensional. So the polymer chain is consisting of such a zigzag structure, and this one is flexible, so bend at the many points, and then the polymer chain can bend uh, each point and can form the amorphous structure that is also called as a random coil. And in some case, for example, in the case of the polyethylene, polymer can form the crystal phase. So in the case of polymer, the crystal, almost the case, the crystal is, shape of the crystal is like this. So that is lamellar crystal. So normally the polymer chain cannot make a extended chain crystal, but the folding of the polymer chain occurs, and the crystal lamella is formed like this. And the thickness of the lamella is around 10 to 20 nanometers. And this lamella, in some cases, this lamella can grow from the nuclei to the radial direction and make the spheritic sphere shape. And this one is called as spherulite. And this one is a polarized optical microscope image of polyethylene spherulite. So maybe that is different from the ceramics or the metal materials. And I told you that the polyethylene can form the amorphous structure and also crystal structure. So let's start from the amorphous structure. So this one is a molecular dynamics simulation of polyethylene at the room temperature. So maybe it's difficult to see, but the gray part is carbon and the white part is hydrogen. And in the bulk state, you cannot see the molecular chain. So I extracted only single molecule from this bulk structure. But So, so let me see the movement of this one. This one. So even at the room temperature, the molecular chain moves. Yeah, of course, this one is a simulation, not the actual molecule, but even at the room temperature, molecular chain can move around. Yeah, because the at the room temperature, polyethylene amorphous part is lava state. And from this figure, maybe you can see that molecular chains overlaps each other. So in the bulk state, so polymer chains entangle each other, and entanglement of the polymer chains are also important for the mechanical property of polymers. And next, this one is a crystal structure of polyethylene. And this figure is electron micrograph of polyethylene single crystal. So normally, in the case of polymer, you cannot get that single uh, crystal. So when you melt the sample and cool to the crystallization condition, so this sample is made.
Sorry, Professor.
Yeah.
We think that you are sharing the wrong PPT because
We're still on page 3.
we're still on
Oh,
page
really?
Oh,
three.
okay,
Really?
okay.
Oh, I'm sorry.
Thank you, thank you.
It's which one? Three.
Now it's 4. Now it's 4.
Okay.
Fine.
Oh, I'm sorry.
Thank you.
So the slide doesn't work. So okay. So should I start from restart from the page 4, or which slide should I?
I think page 4 is fine.
Okay. I'm
So,
sorry.
sorry.
Yeah. So I'd like to use the animation of the PowerPoint slide, but okay. So from here, I'll use this uh, image. Okay. そう okay. Okay, so when, this one is a two-dimensional chemical structure of the polyethylene. But this polyethylene, polymer is a three-dimensional uh, molecule. So this one, polymer does not show the linear structure, but the flexible, bended structure like this, and can form the amorphous structure like this. That is called as a random coil. And this, under certain condition, the polymer can also form the crystal structure. And this one is called as lamella structure, lamella crystal structure. So normally, in many cases, polymer crystal is like this. And polymer chain fold like this and form the ordered structure. And this lamellar crystal also grows from the nuclei to the radial direction like this, and forms a spheroid, sphere shape one, sphere shape crystal. That is consisting of the lamellar crystal. And this picture is a polarized optical micrograph of polyethylene spheroid. Okay. And this one is a molecular dynamics simulation of polyethylene at room temperature. And this one is bulk state of the polyethylene. So there are many, this one include many polyethylene molecular chains, but maybe you cannot distinguish each molecules from this picture. So I extracted only one only single molecular chain from this bulk state. That is this one. So at room temperature, the temperature fluctuation is not so high, but molecular chain also move around even at the room temperature in the case of polyethylene. And as you can see, the molecular chain of the polyethylene is bent at the many points and forms a random coil shape. And in the bulk state, this molecular chain overlaps each other and entangle each other. So such an entanglement between the molecules are also important for the mechanical property of the polymers. And the next slide is about the crystal structures of polyethylene. So this figure is electron micrograph of polyethylene single crystal. So normally when we make a crystal structure in the polymer, once we melt the polymer at the higher temperature and cool down to the lower temperature, lower than melting point. But in such a case, we cannot get a perfect crystal. So it's very difficult to get the single crystal. So this picture, this sample is made from dilute solution of the polymer. And from this sample, crystal structure was analyzed. And this one is crystal lamella structure. And in the lamella structure, chain folding occurs. And the chains are packed each other regularly and form the crystal. So this one is side view of this lamella, and this one is top view of lamella. So from the side view, you can see the polymer molecule packed each other regularly, and from the top view, such a structure is formed. And as I told you previously, this crystal lamella can form the spheroid. So I'd like to show you the crystallization process of the polymer, melt polymer. At first, I'd like to show you the in the case of the polyethylene, but I don't have the movie of the crystallization process of the polyethylene. So I'll show you the in case of the PTT, polytrimethylene terephthalate. That is very similar with polyethylene terephthalate. So the feature of this one is trimethylene terephthalate. So if the number of here is 2, that is a PET, polyethylene terephthalate. And in this, by using this sample, I tried to make a spheroid at the higher temperature. So this figure is a temperature condition to observe the crystallization process of PTT. At first, the temperature, I heat the sample at the higher temperature around 280. That is higher than the melting point of the PTT. And after that, quench the sample below the melting point. That temperature is around 160 degrees Celsius. And just after quench the sample, I observed the structure morphology of the polymer under the optical microscope. And this one is a polarized light microscope image. So let's see the formation processes of the spheroid. So this one is spheroid. So when the time progresses, the spheroid grows grows each other and collide each other, so the boundary becomes linear. Like this. So when you observe the crystal structure under the optical microscope, the image becomes like this. So each these parts are each spheroid, but they collide each other, so the boundary becomes linear, and the morphology becomes like this. And these spheroids, each spheroids are consisting of the lamellar structure. And from this picture, maybe you can see the whole of the sample crystallized. But in the case of a polymer, the crystallinity of this sample is not 100% because when you see the lamellar structure, and this one is the lamellar structure, and between the lamella, there are amorphous regions. So in order to structure exists between the lamellar structure. So when you crystallize the polymer, you cannot get the perfect crystal, but the some part is crystallized, but some part is amorphous region, like this. So in the case of polyethylene, maybe the highest of crystallinity of polyethylene is about 90%, not 100%. And for example, in the case of polyethylene terephthalate, PET, the highest crystallinity is around maybe 60%. So 60% of crystallized PET is crystal, but 40% is amorphous part. So normally the polymer, crystallized polymer is consisting of the both part, crystallized part, amorphous part. That is very important point of the polymer. So, and okay, so and I told you that the molecular chain of the polymer is consisting of the covalent bonding, and in general, covalent bond strength of the covalent bonding is higher than the metal bonding or ionic bonding. So you make an ordered structure like this, so you can get a very strong property. So, and for example, say when you use aramid fiber, when you make aramid fiber and make such a structure, so you can use that one for the bulletproof best like this. That is a very famous polymer or having a strong property. And maybe, as you know, the polyethylene packing string is also strong property because when you apply the stress for this direction, it's very hard to break the film because the molecular chain ordered this direction. But when you apply the stress to this direction, you can easily split the sample because between the polymer chain, there is a weak, weak interaction between the molecular chains. Van der Waals force is interaction is van der Waals force that is very weak, weaker than the covalent bonding. So in this case, this direction is very strong, but this direction becomes very weak. And okay, and let's think about the volume change depending on the temperature. So before thinking about in the case of the polymer, let's start from the case of the water. That maybe that is very familiar with you. In the case of water, at the lower temperature, that is in the solid state, that is ice, and you heat the sample, increase the temperature, the volume slightly increase, and at the melting point, the polymer, water volume increase suddenly, and it becomes a liquid state, liquid water, and when you increase the temperature, the it at the boiling point, it becomes a gaseous state and becomes a water vapor. That is normal one. So water has three state, three phases, and so in the case of semi-crystalline polymer, for example, polyethylene. Now I say that semi-crystalline. So because as I explained to you, the polymer, crystalline polymer is consisting of not only the crystal part, but also the amorphous part. So normally the polymer is called as semi-crystalline polymer. And under the lower temperature, the polyethylene is a solid state, crystal state. And when you increase the temperature, the volume changes, and at the melting point of the crystal, the volume is increased suddenly and becomes a liquid state. That is almost the same with water. But in the case of polymer, polymer doesn't have the gaseous state because polymer chain is very big and very long chain. So before it take a gaseous state, molecular chain decompose and becomes smaller molecules and evaporate. So that is not the polymer. So normally the polymer has doesn't have the gaseous state. Before the becoming the gaseous state, normally the polymer decompose and becomes a smaller molecules. And but in some case, in the polymer doesn't have the crystal state. For example, maybe you know PMMA, acrylic resin, polymethyl methacrylate. So all of you use this one, acrylic desk partition, that is made of the PMMA. And polystyrene is also familiar one, and that one is used for the cases of the optical discs or the yes, and they are normally the amorphous polymer that they cannot form the crystal. So in such a polymer, at the lower temperature, the structure is amorphous, but that is have the solid state. That is called as glassy state. So like glass of the inorganic glass, like inorganic glass, that one can have also glassy state. And when you heat the PMMA or PS, the glass at the glass transition temperature, the radius of polymer chain can move around this temperature, so change to the Lavally state. And when you increase the temperature, the volume increase, and this one also cannot take a gaseous state. So you should remember that some polymer can crystallize, but some polymer cannot take a crystal phase, amorphous one. So structure is totally amorphous. But when you cool down the polymer, the thermal fluctuation becomes lower. So at the glass transition temperature, that becomes around almost solid state. That is called as glassy state. Okay, so from here, I'll explain about the plastics. What is plastics and what is rubber? Maybe Professor Nakajima may explain around this one, but I didn't check his lecture, so let me introduce this one. This figure is temperature dependence of the elastic modulus of polymers. For example, in the case of polystyrene, this one, that is a glassy polymer. So at the lower temperature, this one is a glassy state. And the glass transition temperature is this one. Glass transition temperature of polystyrene is about 100 degrees Celsius. So below this temperature, polystyrene is glassy under glassy state. So at the room temperature, the polystyrene is solid state. And heat the sample above the Tg, the elastic modulus becomes lower, and you can easily change the shape of the sample and mold. Such a polymer is called as plastics. So at the room temperature, the sample is solid state, but at the higher temperature than the Tg, that can change the shape, plasticized at around the Tg. So that is called as plastics. And that is amorphous in the case of the amorphous polymer. And in the case of polyethylene, that is a semi-crystalline polymer. In the case of polyethylene, glass transition temperature is very lower than the room temperature. That is around below the 100 degrees Celsius. So the around this temperature, elastic modulus polyethylene slightly decrease, but the PE is crystallized. Yeah, of course, this one contains amorphous part and the crystallized part. The crystal part, amorphous part is softened around this part, so the elastic modulus decrease, but almost the PE is crystallized. So still, elastic modulus keeps higher value at the room temperature. And when you heat the polyethylene above the melting point, Tm, of the polyethylene, the elastic modulus becomes lower and plasticized, and you can change the shape of the polyethylene at the higher temperature. So this one is also plastic because at the room temperature, this sample is solid, rigid structure, and at the higher temperature, you can reshape the sample. So the important point for plastics is glass transition temperature or the melting point is above the room temperature. That is very important. And plastics means plasticized. This one can be plasticized. So at the higher temperature, the polymers can be plasticized. So they are called as plastics. And what is rubber? So in the case of, let's think about in the case of polybutadiene, that is a rubbery material. So PB is also a glassy state at the very low temperature. But the glass transition temperature of the lab PB is around minus 100 degrees Celsius. So the elastic modulus decrease largely, and around the room temperature, it becomes lovely state. And if you increase the temperature, the elastic modulus continue to decrease. So at the room temperature, this one is under lovely state. So this material is called as lava. Okay. So an important point of the lava is Tg is below the room temperature. So both plastic and lava are polymers. So the difference between them are solidify above or below the room temperature. That is an important point. So if the solidification occurs at the solid state at the room temperature, if the sample is solid state, that is plastic. But the lovely state, that is lava. That is the difference between the plastics and the lava. And maybe Professor Nakajima may explain this one, but I'll also explain this one. So normally the lovely state polymer is like this. We call that one as a low level. So low level, in the case of low level, that have the amorphous structure. And when you elongate the sample, for example, please imagine the chewing gum. So if elongate and keep the strain for a long time. After that, release the stress. So you cannot, the sample cannot return to the original shape, plastically deform, because the molecular chain can slip each other when you elongate the low level. So when you use the lava as a product, you should introduce the cross-linking point in the lava structure, like this. Orange part is chemically introduced cross-linking point. Under this structure, so when you elongate the structure and keep the strain, and after that release the stress, the cross-linked lava can easily return to the original shape. And this one showed elastic deformation. So cross-linking is very important for lavally materials for using as a product. Okay, so next, let's think about size of the polymeric materials. This one is the measure of the size. So CC bonding, size of the CC bonding is around 1 angstrom. And now let's think about the PMMA. In the case of the PMMA, as an example, the chemical structure of the PMMA is like this. And molecular weight of monomer unit, lipid unit, this part is about 100 gram per mole. And if the molecular weight of the polymer, whole polymer, one molecular chain is 10 to the fifth power, like this, so degree of polymerization can be calculated by like this. Yeah, because whole molecular weight is 10 to fifth power, and one monomer unit is 100. So the degree of polymerization is around 1000. So this one should be 1000. Okay, and normally the polymer is three-dimensional one, and this one is carbon, and these four are, for example, hydrogen. And carbon has four hands and three-dimensionally. So between the two hands, the angle of two hands between the two hands are around 109.5 degrees. So when you make the polymer structure, the polymer can have the zigzag structure like this. Not the straight one, but the zigzag structure. So when you think about the zigzag structure, at first, total path length of the polymer chain. Total path length means this length. Let's think about this length. So distance between the two carbons are 1.54 angstrom, and between the two, no, I'm sorry, the monomer unit, one monomer unit has the two carbon atoms. So this path length is 2 times of 1.54 angstrom, and there are 1,000 monomer units. So total path length is 1.54 times 2 times 1,000 equals 3,080 angstrom. So but this one has a zigzag structure, and the distance between the monomer units are 2.5 angstrom. So in this case, 2.5 times 1,000 equal 2,500 angstrom. So that if you extend the molecular chain, the size becomes around 250 nanometer, around this. And the thickness of your hair is around one order of the 100 micrometer. So the order is completely different from this one. Size of the polymer is around the order of the 100 nanometer. And in the next slide, we think about the size of the random coil of the polymer chain. That is also about the several tens of nanometers. And normally the polymer density of the polymer chain is around 1.0. And when you think about the square root of mean square of end-to-end distance r, this one is the end of the polymer chain, and another end of the polymer chain is here. And theoretically, the distance is calculated like this. M is molecular weight of the polymer, and R is the end-to-end distance of the polymer chain. And if the polymer chain forms a random coil, the end-to-end distance can be calculated from this equation. And now we assume that the molecular weight of the polymer chain is this one. So you can easily calculate the end-to-end distance as 300 angstrom. That is around here. And okay, so please remember that the size of the random coil is around several tens of the nanometer. Okay, and here is when you think about the single crystal lamella, the number of foldings, I explained to you the folding occurs when the polymer chain crystallizes. So 200, 2500 is come from this one, zigzag length of the zigzag extended chain, because in the crystal form, the polymer can take a extended chain form in the crystal structure. And the thickness of the lamellar structure is around 100 angstrom. So one molecular extended one molecular chain is 2500, and the thickness of the lamella is 100. So in this lamellar structure, the 25 time folding occurs for each polymer chains. And each lamellar structure, there are 40 monomers in this structure, 40 monomers between the 100 nanometer region. Okay, and finally, let's think about the size of the single molecule aggregation. That means now let's think about that one molecule aggregate and form the density of 1.0. So only one molecule can find the one molecule aggregate and becomes a density becomes 1.0. So in that case, the radius of the aggregate can be estimated around 35 angstrom. But here you see the size of the random coil is around 300 angstrom. So 10 times larger than this one. So this means that molecular chain does not exist on aggregation of the each single molecular chain, but the molecular chain overlaps each other like this. So I draw the image like this, but actually the other polymer chains overlaps each other and forms a density of 1.0. That is also important point. Okay, so let's change yes, another story. So polymer, I told you that the polymer is consisting of plastics and rubber. But when you mold the sample, you can classify the polymer also as a thermoplastic or thermosetting. So let's start from the thermoplastic polymer. So in the case of thermoplastic polymer, at the lower temperature, the sample can form the amorphous structure or the crystal structure. And when you heat the sample above the gas transition temperature or the melting point, this one changes to the amorphous state and becomes a liquid state. And you can repeatedly change the state between them. So, for example, such a polymer is polyethylene, polystyrene, polymethyl methacrylate, polycarbonate, polyethylene terephthalate, polyamide, and so on. But there is also another type of the polymer that is called as thermosetting polymer. In the case of thermosetting polymer, the starting material is not polymer. That is monomer or the oligomer, the smaller molecular weight one. And when you heat the starting material, they can react each other and form a three-dimensional network structure like this after the heating. And this one is connect each other. So this one is also called as a polymer. But this one is not linear and not have a linear structure, but the three-dimensionally networking structure. So once this one is formed, you cannot return to the original shape because between the monomer unit, so there is a chemical bonding is formed during the heating process. But this one can have a rigid structure. And for example, maybe you know the epoxy resin. Some of you know the epoxy resin. So this one is a two-component epoxy adhesive. Maybe some of you use the epoxy resin as an adhesive. So in this case, you can use a base resin and hardener and mix them. And when you heat the mixed initial material, they can react each other and make a form of the three-dimensional network and becomes a polymer. For example, in the case of epoxy resin, there's epoxy groups in at the both end of the epoxy molecule. That is a base polymer, base material of the epoxy resin, starting material. And when you add the diamine, this one as a hardener, so amino group can react with epoxy group. So at first, they react and form a main chain structure like this. And when you continue to heat this sample, so this one is this one. The amino groups in this point can also react with another epoxy group. So they can form a network structure like this. That is a some setting resin. Case. So when you mold the sample, the some plastic polymer can be easily melt by heating the sample. And for example, injection molding you can do and make a molded sample. And after that, you can easily return to the here. So when you make a strand of the polymer, plastic, some plastic, and make a pellet, you can repeat this part. So plastic material is a renewable polymer. But some setting, in the case of some setting polymer, so during the molding process, the reaction occurs and the three-dimensional network is formed. So you cannot reuse this material. It's very hard to use. So that can be compared to the, for example, in the case of some plastic, you can compare to the chocolate. Chocolate can easily melt and make a shape, and after that, you can remelt and make a shape. But in the case of cookie, this one can be compared to the some setting polymer. That is, if you make a cookie, you cannot reshape this one because this one has a rigid structure and you cannot melt. Okay, and there are many kind of molding methods for the some plastic. And popular one is injection molding. So at first you melt the sample in the cylinder and after that inject the melted sample into the metal mold and cool the mold, and after that you can remove the many kind this plastic with many kind of shapes. And when you make a sheet, you can use calendar molding. And when you make a storage bag or the film, you can use inflation molding. And when you make a hose or a pipe, you can use extrusion molding. And when you make a pet bottle or a plastic bottle, so blow molding is used. And for example, automotive plastics parts are many of the automotive plastics are made by using the injection molding. So for example, the front bumper of the car is also made by using the injection molding. So this one is a metal mold, and normally the metal mold, the temperature of the metal mold is lower than the crystallization temperature. So when the sample is injected into the mold, that this sample becomes solid and easily removed from the mold. Okay, and in the case of the some setting polymers, molding method is different from the plastic one. But the important point is starting material of the some setting polymer have the low viscosity one. So you can pour into mold or the laminate the sample to the mold. And after that, heat the sample so the reaction occurs, so you can get the molded sample. Okay. So, okay, so let's move to the next stage. So let's think about the mechanical property of the polymers. So this figure is a stress strain curve of the polymer. Stress strain curve means when you mold the sample like a dog bone shape like this and elongate the both ends. So you can draw the graph of the strain and the stress. So if the polymer is brittle, the strain, at the lower strain, the stress becomes higher and breaks. But in some cases, for example, polyethylene, this one is ductile. So you apply the constant, you apply the strain, the stress becomes higher, but around a certain stress, so this one can elongate and breaks at the higher strain. So such a behavior is called as ductile. Both are the case of the plastics, but in the case of rubber, in this plot, the slope corresponds to the elastic modulus. So in the case of rubber, the elastic modulus is very low. So the curve becomes like this, and the rubber can elongate too much, so elongate largely and breaks like this. And the important point of in the case of the plastic is brittle ductile transition can be occurred at the higher temperature because around the glass transition temperature, the sample becomes soft. So brittle materials at the room temperature can be softened and becomes ductile. So the property depends on the temperature, like a rubber. So temperature is very important when you think about the mechanical property of the polymer. And in the case of polymer, the polymer have the viscoelastic properties. Viscoelastic means this one have both property of the elasticity and viscosity. So when you think about, for example, chewing gum, when you elongate the chewing gum rapidly and rapidly release stress, the chewing gum can return to the original shape. That behavior is elastic. But when you deform the chewing gum slowly, and after that release the stress, the shape doesn't return to the original one. Yeah, of course, some part return length return to the some percentage, but not the original shape. Such a property is viscous property, and so polymer have both properties, and depending on the speed of the deformation, that is very important. So let me introduce a model of the elasticity or the viscosity. At first, let's start from the ideal elastic material. This one is the ideal case. And when you think about the rectangular plastic materials like this, and if the initial length is L0, and when you elongate the sample, the elongation becomes dl. So in this case, stress is defined as like this. So load, applied force divided by initial cross-sectional area. That is definition of the stress. And strain can be defined by this equation. Oh, I'm sorry. So elongation dl divided by the initial length, that is strain. And normally, the ideal elastic body can be represented by the spring, like this. So in the case of the ideal one, when you increase the strain of the sample, the stress linearly increase, like proportionally increase, like this. So relationship between the stress and the strain can be represented by this equation. And the proportionality constant of this stress and strain is elastic modulus. This one. That is elastic modulus. So when you apply the constant stress to the spring, the strain also constant. If you keep the stress at the constant, strain also keeps constant. That is the important point of the spring. Okay. So, and this equation, shape of the equation is very similar with Hooke's law. So force and spring constant and deformation x, that's very similar. But in the case of polymer, we normally use this equation, and proportionality constant is elastic modulus. Okay, so next let's think about the viscosity. So viscosity is resistance to fluid flow. For example, when you think about the stirring the water and let stand, so the flow gradually slows down and stops. During the process, the kinetic energy of the flow converted to heat by internal friction of the liquid. So that means energy dissipation occurs. such a behavior is called as viscous, and such a property is called as viscosity. And ideal viscous body can be expressed by such a model by the dashpot. The dashpot is inside of the dashpot is like this. So please think about imagine that the cylinder filled with liquid, and there is a piston, and the end of the piston there is a disc with small holes. So when you move this piston to the, for example, upward, you can move this piston, but the hole is very small. So you cannot move this one largely, but you can move the piston slowly to the up direction. That is a dashpot. And when you stop the piston, you don't feel the force from the liquid or from the dashpot. That is also important. So in this case, stress can be represented by this equation. So stress of the viscous material is proportional not to the strain but to the strain rate. This one, because when so please imagine that when you put your hand in the water and push the water, so during you pushing the water, you feel the stress to your hand. But when you stop the hand, you don't feel the stress. So important point is strain rate, but not the amount of the strain. So in the case of viscous material, the stress is proportional to the strain rate, and the proportional constant is called as viscosity. And in this case, strain is represented by like this from this equation. No, not strain. I'm sorry. This one is viscosity. So strain is same with that one. Strain is gamma. Okay. I'm sorry. So, but the important point is stress is proportional to the strain rate. That is very important for the viscous body. So if you, for example, if you apply the constant stress to the sample, you cannot deform suddenly and slowly deform the sample. So the strain gradually increase like this. That is a very important point of ideal viscous material. Okay, so let's think about the behavior of the polymer by using such a two kind of ideal models. So now let's think about considering the behavior of strain when constant stress is applied to the polymer like this. So for example, this one is a polymer film. Please imagine that this one is a polymer film, and when you put the weight below the polymer, and after that, how the stress, how the strain of the film becomes. So maybe you can easily imagine that the polymer film gradually elongate. So such a behavior can be explained by the forked model. Forked model is like this parallel model of the spring model and dashpot model. And from in this model, you can make a equation for each part. So when you think about the stress for the spring part, the stress can be expressed by the spring constant of the spring part and the strain of the whole samples. And the viscous component should be like this. So stress for the dashpot sigma 2 can be expressed by the viscosity of the dashpot and the strain rate of this part. So the total stress can be expressed by the summary of them and becomes like this. And when a constant stress is sigma 0 is applied to the sample here, so the equation becomes like this, and you can get this equation. But this equation includes a constant that you cannot know this constant. So now let's think about the initial condition. So when you apply the constant stress instantaneously at time 0, like this, so if you think about the behavior of the spring part, this one can deform instantaneously and strain becomes constant. But this part is dashboard part cannot deform suddenly, so gradually increase. But this model is a parallel model. So in this case, spring part cannot deform because dashboard doesn't deform instantaneously. So strain of this model is governed by strain of dashboard. So the at the time equals 0, when the time equals 0, the strain is decided by the behavior of the dashboard. So the gamma is equal 0. So when you apply this initial condition to this equation, you can get a constant part and you can get this equation. So by using this equation, you can express represent the behavior of the strain at the constant stress. So you can easily imagine that when you apply the constant stress to the sample, the polymer film can elongate gradually like this. So this equation, this behavior can be fitted by using this equation we get from this calculation. Okay. So forked model is used for such a phenomenon. Such a phenomenon is called as creep phenomenon. Okay. So finally, I'd like to introduce another one that is also a famous one, Maxwell model. So Maxwell model is used for the think about considering the behavior of the stress behavior when a constant strain is applied to the polymer. Previously, we think about the when you apply the constant stress to the film and think about the strain of the film after applying the constant stress. But when you think about the the stress behavior when you apply the constant strain at, at time equals 0. In that case, normally you can use Maxwell model. Maxwell model is like this, the different from the forked model. And in this case, when, you can also make a equation like this separately, and you can combine these two equations by using a equation of the strain. And here, you can get this equation from them. But in this case, you should also think about the initial condition of the sample. If so, now B applies a constant strain at the time 0, instantaneously applies a constant strain. That means that if the spring is deformed, only the spring deforms. The spring can deform when you apply the constant strain. So the stress becomes like this. But if you think about the spring doesn't change, but the spot may change. In that case, so if you apply the constant strain, means strain rate is infinity. That means when you apply the constant strain at time equals 0, that means strain rate is infinity. But that is impossible. That situation is impossible. So this means when you apply the constant strain at time equals 0, the spot doesn't change, and only the spring part changes the shape. And so from this initial condition, you can get this equation, and finally you get this equation. So this one can represent the stress relaxation process. Maybe you can also imagine the stress relaxation process when you apply the constant strain at time 0 equals 0. So at first, spring part elongate, but strain is constant. So dashpot can move. So if the dashpot moves, the spring part shrinks gradually. So total stress of the sample becomes lower, and finally goes to 0. So this behavior can be expressed, represented by this equation. That is Maxwell model. So the summary of this part is viscosity is no polymeric material shows the viscoelastic properties. That is the combination of the elasticity and the viscosity. So elasticity is stress generation due to strain, but viscosity, in the case of viscosity, stress is generated by the strain rate. That is very important. And when you apply the strain at high strain rate, so the polymer behaves more elastic one. But when you apply the stress or the strain at a slow speed, So this one behaves more viscous because dashpot at the short time, the dashpot doesn't work, and only the spring part works. But at the after the longer time, the dashpot behavior is very important role for the polymer. So the speed is very important for the behavior of the polymer. Okay, so today I prepared up to this slide. That's all. So there is around 10 minutes. So is that okay? So do you have any questions?